Okay, so this problem says, suppose that p sub 0, remember typically what this script means is that it's the value of p whenever its variable is at 0. So what is the value of p whenever, now if you notice, if you look down here, it looks like we're talking about a function of time. So p sub 0 just means the p value when time is 0. So it says that that amount is invested in the savings account in which interest is compounded continuously at 6.7% per year. That is, the balance P grows at the rate given. So now we've already talked about what this continuous growth model looks like, and this is another way of expressing that. So they're giving us what's called a differential equation. There's lots of these. However, this particular differential equation is very important to the number E and to the notion of continuous growth in general. So let's just look at this real quick. What it says is, we have a derivative, right? Notice this is in the form of a derivative. It says dp dt. So it says the rate of change in P with respect to T. So perhaps this is the P, meaning the money in the account, with respect to time, being the T. So the growth rate of P with respect to T is equal to some percentage of P itself. Look, the growth rate is exactly 6.7% of whatever the function's value happens to be at that time. So that was what's considered, that's what makes it continuous growth, right? Its growth rate is equal to some percentage multiple of itself. So we know that the equation that satisfies that particular differential equation is the PERT formula, or the continuous growth model. In this case, they want you to write P sub 0 as the P value. So it would be P sub 0, right? E, of course, the growth rate is that 6, 7, and then we have the T. And this is the form that we need to use for generate a function that's going to satisfy this condition here, this differential equation. Now watch, if we take this derivative, remember the way you get the derivative of a function of this form is to rewrite it. So we do P sub 0, e to the 0.067t, and then remember you would multiply by the derivative of its exponent, which since it's linear is just going to be that 0.067. So this here's the derivative, right? Look, this is dp dt. Well, if you notice, dp dt is the exact same thing as p of t. It's just multiplied by that 0.067. So it's the nature of how this derivative arises here as a constant multiple of itself that allows it to satisfy this differential equation. Now, as far as what you need to know to get through the problem, maybe a lot of that sounds convoluted, but it really comes down to conceptualizing what this continuous growth function really does, this PERT formula. The reason why it's so special, or at least one depiction of it, is that it is a way of satisfying this differential equation. We need a function whose derivative is, I don't know why I erased all of that, I'll write it again. A function whose derivative is exactly 0.067 multiples of itself. Right, so anyways, put that back. We said P of t was equal to P sub 0 e to the 0.067t. That's decimal right there. Okay, so now at this point it says, well, suppose $15,000 is invested. Okay, so we just want to know, oh, actually, I'm sorry, after a time value of 1 year. So let's suppose for 1 year we're investing $1,500. Well, that's that P sub 0. That's the initial investment. That's where it starts. And then e to the 0.067, plug in that 1 there. And I'll let you do that. I'm sure that's something you can calculate easily in the calculator. And then for C, remember, you could set this up. You could set this thing, of course, it would have to be a T, right? We are investing $1,500. E, we've got that growth rate. And the question is when, so we got a T value, is it going to be double itself? Well, remember, if we're doubling, we can approach this two ways. You can just continue with the model, right? 1,500 is going to be 3,000. And then you can divide out the 1,500. Both sides divide by 1,500. And then we get this piece here. And then you write this as a logarithm. So we've got the natural log of, remember, the logarithm is always equal to the exponent. and this is the answer to the exponential statement. It goes in as the argument for the log. So at this point, you would just divide by that 0.067, and that would be the answer for that problem. Remember, I did give you a shortcut for doubling time. Remember, doubling time is always the natural log of, in this case, the ratio we're looking for is 2. We're doubling, right? Put the 2 there, and then divide by the growth rate. So if you had this shortcut in mind, you could just do ln 2 divided by the 0.067 from the get. So anyways, hopefully that helps. I think the main reason why this question was asked was because of the form of how they were presenting this PERT formula here. So hopefully that helps. And again, if you have any more questions, let me know. Thank you. Bye.